Hi guys, we're moving on to the next unit here, which is work, energy, and power. So I wanted to talk about those today, especially work today. So when we're talking about work, we have a lot of different definitions of work in normal conversation. We can talk about it like I have to go to work, like it's a job. We can talk about it um, as a career. Most often we talk about it as a measure of effort. So I worked really hard at that and did those different things. Work has a very specific meaning in physics, and that meaning is uh, when something does work, it means there's been a force that has caused something to move. So there has to be a force and a displacement. And so that is our definition of work in physics. So I could push for hours on this desk in front of me until I'm sweaty and cramping up and say, man, I worked really hard to try to move this desk. And if it didn't move, technically speaking, I did not do any work by the definition of physics. So something has to be moved. It cannot exist. Work does not happen when something's not moved. All right. Our formula for work is simply force times displacement times cosine theta. Now, I don't know why we don't use delta x for displacement or x for displacement. We use d just to throw in yet one more variable. But so work is measured by taking the amount of force and the displacement that that force has experienced or has caused the object to experience. So force is in newtons, displacement is in meters, of course. The angle theta is the angle between the direction of the force and the direction of displacement. So when we have something that has a force put on it at an angle compared to where it moves, we have a situation where not all of the force is doing work. So let me show you an example here. Here we have a object on a surface that is being pulled along the surface at an angle. Maybe it's connected to a rope or something, and it is looking like it is moving from the left to right, but the force is up at an angle. So that force up at an angle, some of the force causes the block to move from left to right, but some of the force would be pulling the block up. Well, we know the block doesn't go up. So the force that causes the block to go up is really not doing any work because there's no displacement upward. So only the force that's parallel to the direction of motion does work. So that means that the component of force in the horizontal direction, in this case, does work. So we would use F cosine theta, for example, and that's where the F and the cosine theta come from the work formula. Now notice there's another form of work being done, and that's done by friction, because friction is parallel to the direction of motion, but it's in the opposite direction of the direction of motion. That will come into play when we talk about the sign of work. So friction in this case is doing negative work. In fact, friction always does negative work because it always works against the direction of motion. All right. So if we look at this formula and simplify it here, if we were to break stuff down into forces, perpendicular forces and components and stuff, when we look at the force in the direction of motion, we take only that force, so we can take cosine of the angle. And when we know that, we can then just say force parallel to the direction of motion or to the displacement is work. So FD is work. All right. We can also break it down even more because force is mass times acceleration. So MAD times cosine theta is if we know the mass and the acceleration. If we know the net force, then we can just use the net force. Okay. Here's an example of work being done vertically on this. So work is done on this car by water, so the force times the displacement. Well, in this case, displacement is vertical, so we can talk about it in terms of height. So mgh, m being the mass, g being the acceleration, and h being the height, or mg being the weight and the height. So the work done vertically is just taking the weight times the height. all right? So, of course, this could only happen in Russia, I suppose. I'm sure you can do it somewhere else, but this video shows us a car being lifted by multiple fire hoses. Um, it's just there for entertainment purposes. We're not going to measure anything, but it's interesting that water is doing the work to move the car up. Now, of course, that at some point, the water and gravity are equal to each other, so net force is zero at this point. And then they shut the water off, and the gravity starts doing the work, and it accelerates it downward. So we have different aspects of work being done in different ways, horizontally or vertically. Vertically, we have to do work either with or against gravity. So that's something to keep in mind. Here I have a nutrition label from orange juice, and we can see that energy is measured in kilojoules and kilocalories. Work is measured in Newton meters or joules. All right, and that's why I put this up here. The kilojoules tells us how much energy is available in that serving size of orange juice. And energy and work actually end up being the same thing. And we'll look at that later in the unit here. But we look at work in Newton meters. I like to use Newton meters because I think it's more descriptive because it tells us force and displacement. But you can also use joules to describe that. You might remember using joules in thermal chemistry. And that just tells us how much energy was broken or formed in bonds of chemicals. We use joules in energy in all different types of energy, including thermal energy, but we're going to be using mostly mechanical energy, which is energy due to motion or position of objects. All right. But usually when I talk about work, I talk about Newton meters. When I talk about energy, I talk about joules. You might hear me interchange the two terms, and which is appropriate in work, but usually we don't use Newton meters in terms of energy. So it's an interesting dichotomy there in that we use Newton meters in terms of work, but not energy, but we can use joules in work or energy. All right. Work is not a vector. It is a product of two vectors, force and displacement, but it only happens when the vectors are in the same direction, when a component of each vector is in the same direction. So when we talk about work, the sign of work tells us or allows us to predict what happens as something moves. So the sign of work is when the force and the displacement are in the same direction, it's positive. And when the force and displacement are in opposite directions, the work done is negative. Positive work means something is going to speed up, speed-wise, not velocity changes only in terms of speed, not direction. Okay. Negative work means the speed of the object is going to decrease. So remember, speed is not a vector, it's just a numerical magnitude. So work changes the magnitude of velocity, not the direction. So a force perpendicular to an object's motion does not do any work. It changes the velocity because it changes the direction, but it does not change the speed. All right. Friction always does negative work because friction always opposes motion. Okay. If we have work times displacement, if we were to graph out displacement and force, the area underneath the graph is the amount of work. So work is an integral of force versus position, if those of you that are in calculus. So it's just an area. That's great if the force is constant. What if the force changes? What if we have a changing amount of force? Well, that changing amount of force based on where something is will cause the graph to change slope. And so it's a little bit more difficult. So if we can make the increments smaller and smaller, we get a nice curve. And those of you in calc and pre-calc have probably seen things like this, these small intervals between spots. And the smaller the interval, the the more accurate we get, so we don't lose some of those areas that we have in the left-hand graph with the right-hand graph. All right. A typical object that has a changing force based on displacement is a spring. So this shows us two different formulas for springs. The first formula is Hooke's law. And Hooke's law tells us that the farther a spring is from its rest position, the more it resists. The negative just tells us that the displacement and the force are in opposite directions. So if I have a spring and I stretch it out in this direction, it's going to be pulling back in this direction. And the farther I stretch it out, the more it pulls back. If you've ever shot a bow and arrow, you know that the farther you pull back the bow, the faster it shoots the arrow because it puts more force on it. We all have that understanding. If you jump on a diving board, the more you bend it, the higher you get. So springs always resist with more force the farther they are from their rest position. And Hooke's law tells us how much force that is. It uses F equals negative kx. The negative just tells us x and F are in opposite directions. The K is a constant. It's called the spring constant. It measures the stiffness of the spring in newtons per meter. How many newtons it takes to stretch or compress a spring 1 meter. All right. We might do a lab on Hooke's law at a later point in time, but this is just establishing what happens when we stretch a spring and how much force it changes with. So the force and the change in displacement are related to each other. The bigger the change in displacement, the bigger the force. So that goes back to, and we see this graph here then. If there's no change in position, there's no force. It doesn't resist anything. But as soon as you go either compressing or stretching a spring, it's going to start resisting. And springs, metal springs, have a constant, and that's a slope that we see here, right? Because it's got a constant, if we go back to that last thing here, the force and position changes. So that area is a little bit harder to find. To find that area, we now have a formula, 1/2 kx squared. So that tells us how much work is done on a spring to stretch or compress at a certain distance if we know how stiff that spring is, the spring constant. It also tells how much work can be done by a spring if it changes a certain displacement and we know how stiff that spring is. Springs are a way to store energy. So we'll use this formula later when we talk more about energy as well. All right. So when we talk about work done, we can look at it in terms of force and distance in normal situations, or we can look at it in situations where the force changes based on the distance, and that's using this spring energy formula, or the work formula for a spring, 1/2 kx squared. All right. That's where we're going to stop today. I have a couple of questions for you guys to review and work on with springs and with work. And we will talk tomorrow about energy. Thanks a lot. See ya.